Okay, secondary clay minerals. So today we are going to read another simple subject, simple concept called secondary clay minerals. Probably these minerals plays a major role in our fertility status in our agriculture farm fields. So we will see today what are the secondary minerals and what are their roles. And before that, we will see some basic concepts and we will see some introduction regarding these secondary clay minerals. So generally, students, these secondary clay minerals are completely derived from the pre-existing primary minerals. So primary minerals, we have seen some concepts. We have discussed some concepts in rocks and minerals. We have seen in those in last class we have discussed. We have learned something about some. So we have came to know some words of primary minerals. So from those primary minerals, these secondary minerals have been derived by some changes or some changes in the pressure or some climatic conditions, some temperature conditions. We get the our secondary minerals. So in the secondary minerals also, we can see two types. One are silicate minerals and another non-silicate minerals. Non-silicate minerals are completely oxides. So non-silicate minerals are completely oxide. They're oxide in forms. We can see some iron oxides, magnesium oxides. So all these oxides comes under non-silicate minerals. Whereas silicate minerals, here we can see some sheet minerals. You can see some tetrahedra, octahedra sheets. You see those type of two types of sheets we can see. So today class we confirm this silicate tetrahedra, silicate minerals. So silicate minerals are completely contains a more amount some silicate contains silica and with combination of with other elements. This is the secondary mineral. So primary we have to remember what secondary minerals are derived from the primary minerals, and these secondary minerals are of two types, majorly silicate minerals and non-silicate minerals. We will read in detail about the silicate minerals. So what we are going to read? This is what. So naturally, students, how a silica tetrahedra looks. It will looks this, like this. So totally there will be four oxygen atoms will be there, and one silica tetra silicon will be there. So remember, what is the charge of oxygen? Students, what is the charge? So charge is minus 2. So here minus 2, here minus 2, here minus 2. They're totally 1, 2, 3, 4. 4 twos are 8. So totally
Eight.
minus 8 charge is there. So silica tetrahedra will satisfy, will have a 4 positive charges. So to attain the geometric structure, to attain some crystalline structure in nature, so it will satisfy each one charge. So naturally, how much balance of charge is there? We can get the minus
Minus
4
four.
charge
Four.
is there. So there will be excessive negative charge. So actually this negative charge is it plays a major role in fertility cell, because due to this negative charge only we can attract our cation minerals. Naturally, most of the plant nutrients are cations, except some nitrate form like that. So except nitrates and some phosphates are, except in some exceptional case, most of our nutrients are in cation form. This is the reason why. And also students, to satisfy the surrounding charges, some oxygens will be shared by the another tetrahedron side by side. So by sharing and sharing, we will get one sheet. What is the sheet? Now I'm going to show in my animations. So here this is one tetrahedra with some silica, and this, so both will share, both the structures will share one common oxygen. So naturally charge was satisfied. And students, remember, while this sheet silica tetrahedral sheet will be share oxygens with octahedrals. We will discuss that concept in our next slide. So this is the natural, this very easy structure. We will see this actually is a very fundamental structure for the formation of clay minerals. So what next? General geometric positions. What are those? There is, we can see now this theory is for your reading purpose. Geometrically, it is a purpose of arraying. Now there will be four oxygen atoms with a radius of 1.32 angstroms with a central cation, which I have already explained. It around 0.42 angstroms. So touching all the each corners. And also to attain the neutrality, what will do, just whatever I explained, it is in a theoretical form. You can read this for reading purpose. Okay, it will satisfy each one's charge. So to attain the complete consistent crystal lattice, what it will do? So adjacent tetrahedral unit will will share the oxygen atoms from side by side. So what will happen? So ultimately they will attain what will happen? It will attain some neutrality, and you can see some silica tetrahedral sheet form. So it will extend up to a norm. It will continue like this. So naturally, what will happen? It will end up with one negative charge. So that is the reason why silica tetra, some claimant, all the secondary claimant rules are in negative charge. This for understanding. Okay, students, this is regarding the silica tetra structural unit. This is a very fundamental structural unit. It has a 4 oxygen atoms consisting of 2 minus 2 minus 2 some charge. So there is a totally there are 8 minus charge, only 4 is there. So 4 is satisfied, so excess negative charge will be there. To satisfy that, what will happen? It will again tie up with or bond with adjacent tetrahedral unit. So naturally we can see some a long sheet. That sheet is called silica tetrahedral sheet. So this is a silica. This is regarding the silica tetrahedra conditions. Coming to the next student, our aluminum octahedra. Naturally, students, we can easily identify our silica tetrahedra, but aluminum octahedra is not so like that. It is somewhat very difficult. It's octa. What is the meaning of oct? What is the meaning of oct? Come on, you should answer, students. What is the meaning of oct?
8.
Yes, oct means 8. 8 means this 8 indicates what? Aluminum octahedra. Oct means 8. You're right. So, what is the meaning of this 8 or this oct? What is the meaning? Students, you have never seen this
Sir,
question.
hydroxyl ion.
No, not that. Anyone, please? Octa means 8. You're right. So what is the meaning of that 8? SRF students, you should answer. Okay, no one is answering. I'm going to answer. 8 means 8 sides. See, students, there are totally 1, 2, 3, 4, 5, 6. So 6 OH minus ions, or sometimes oxygen, mostly OH minus ions. There will be OH minus ions here. In central, naturally, there will be aluminium, mostly aluminium. Sometimes there is a chance of magnesium also. This is a chance. So octa means 8 sides. How many sides? 1, this backs at 2, 3, 4. This 4, top 4, down 4. So totally 4 plus 4, 8. So totally there are 8 sides are there. Actually, sites have a lot of meaning, students. If you have seen my previous class on crystal chemistry or crystallography, I've given some basic structural images, sites A, B, C, and some angles of alpha, beta, gamma. So you can apply that concept here. But to know, if you want to more knowledge, you have to go in depth regarding that subject. Anyhow, coming to our class, here is another basic building block, students. That is the aluminum octahedra. This aluminum octahedra also will share its OH minus ions. Generally, students, oxygen has how many? 1 minute. How many? Oxygen has how many? Oxygen will have minus 2. Okay. Oh, sorry. Oxygen is minus 2. Okay. But this minus 2, when it join with H plus ions, what will happen? One charge is satisfied. So OH
H2O.
minus ions.
OH minus.
No.
OH minus.
OH minus. There's only one oxygen is there. That oxygen charge is 2 minus. H plus. Here one positive charge is there. So this positive charge will satisfy one negative charge. So ultimately, when combined with oxygen ion and hydrogen ion, it leads to the formation of OH minus ions, hydroxyl ions. That is what happening here. Here will be one OH minus. Here will be some OH minus. See, here also will be one OH minus. Here also will be some OH minus, like that. Okay, here also will be one OH minus. So 1, 2, so totally 6 is there. But our aluminum is 3. Only 3 is there. Two charges here due to because aluminum is, we have only 3 positive charges. So what will happen to satisfy its excessive negative charge? So there is excessive minus 3 negative charge is there. To satisfy that excessive negative charge, it will bond with adjacent tetrahedra, but not like in tetrahedra there is only one oxygen sharing is there. But in octahedra, aluminum octahedra, you can see two There will be sharing of, see this one, there will be two sharing of two oxygen, two OH minus ions will be taken place. So there will be two excess, there will be two sharings will be there. So this is the major reason. So understanding aluminum octahedral structure for a very early student, it is somewhat difficult, but most of you have some idea regarding this aluminum octahedral structure. So by satisfying like this, we will go place. But students remember, why it was sharing two OH minus ions with aluminum. So by satisfying like this, we will go place. But students remember, while it was sharing two OH minus ions between the octahedra, when this complete sheet was going to share or forming some sheet clay mineral or sheet minerals, or our silicate minerals, or it joining with aluminum, this silicon tetrahedral sheet, it have to form some bonding. It will form some bonding, weak bonding with oxygen of that structure. Which structure? Silica tetrahedral structure. So that bonding between the oxygen atoms is the main reason why the structure was stable and strong. Naturally, students, this is one view, students. But if you want to see this upper view, how it looks, it will be looks like this. Now I will show that animation. It will be look like this. See, it will be look like this. Probably you are much familiar with this diagram in your textbooks, in your BSc textbooks. This is the side view. This is upper view. If you see some upper side, you can see this type of bondings will be there. This type of structure you can see. But overall basic structure, this is what. This is what regarding aluminum silicate. So naturally, students, here also there is excess negative charge is there. That was the only half is satisfied by the aluminum, but at the same time, it will combine with the adjacent octahedra to satisfy its negative charge. So what will happen? Then the neutrality will be achieved. So like this, by sharing of again and again aluminum octahedra, we can get our aluminum octahedra sheet. One sheet will we get. So by combination of those two sheets, which sheet? In the previous slide I have explained about the silica tetrahedra sheet. Now I'm going to explain the aluminum octa. Now I have explained the aluminum octahedra sheet. By combination of these two sheets, we get different secondary clay minerals. Those are very important for agriculture purpose also. How? Because you can see the lot of Cs is depend upon these clay minerals. Cs is completely different from one mineral to one mineral. If the same type, this was replaced with magnesium in magnesium 2 plus, right? So what will happen? There will be excessive negative charge will be there, more negative charge. So more negative means there will be more cation action capacity will be there. So that is the reason. That is a different student. If that is a chart that you will learn in chemistry, isomorphous substitution, etc. You will learn in that subject. So for up to now, you just learn what is octahedral sheet, what is silica tetrahedral sheet. So this is regarding a small explanation regarding the silica tetra and aluminum octahedra, students. Now we will see how we are going to deal about. Next slide, we are going to say another different concept. What is that? Yeah, you can see it will sharing will be there. Two oxygens will be two OH minus and sharing will be there. This is what I'm representing here. Here it is very difficult to see you. All of for early students, it is very difficult. But here in this view, you can see only there will be sharing of two. There will be two sharings will be there. You know, two OH minus ions will be sharing will be there. So regarding this, as I said, by this tetrahedra, octahedra bondings together by sharing oxygen atoms in the different layers. So you can see, we can see these both these tetrahedra, octahedra will share the oxygens. So it will form some oxygen bonding between these two tetrahedra, octahedra. So that sharing will keeps the layer in that those layer or clay mineral in a very stable form. Will keep very strong form. So these combinations of these two will give different physical properties we can get in the soil, and we can get the different chemical properties in there by combination of tetrahedra and octahedra. But how many types are there? Silica tetrahedra. That silicate clay is nothing but lattice layer silicates. So we can see this is a very common 1:1 type. Example is kyanite and halloysite. And at the same time, 2:1. 2:1 we can see montemorillite, illite, and vermiculite. But vermiculite is limited expansion, students. Can anyone explain why? Can anyone explain? Vermiculite is also expanding type, 2:1 expanding type only, but it has one limitation, that is limited expansion type. Why? Why reason? Is there any reason? Okay, fine. At least after completion class we may
Sir,
answer. And coming to
it didn't absorb more water.
It won't absorb water. Okay, but dude, there is a common. Not exactly like that. It also has in between the interlayers there is some potassium ions also will be there. With the help of water molecules, some potassium also will be there. That is the reason why it will have some limited expansion will be there in vermiculite. Is it clear, students? Okay, I hope so. Anyhow, 2:2 type is chlorite. Example is the 2:2 type means additionally we get another some lattice structure. We will see in the coming slides why chlorite is called 2:2 type. This is the these are different types is there, and 2:1 we can see some 2:1 in 2:1 also the two types is there. Expanding type is there, non-expanding type is there. We will discuss all those things. So based on the layers, arrangement of layers and the bondings, etc., etc., we will get this type of clay minerals. Now we will see what are those. Right, kyanite. Yeah, students, this is a kyanite. It's a 1:1 type of mineral made up of what is that? One silica tetra, aluminum octahedra. So it is made up of one silica tetrahedron. We can see we can see one silica tetrahedra, one aluminum octahedra will be there. So this is for understanding. But as I said, students, see students, there will be a common bonding. See, even it was mentioned here also. Some common bonding will between there. This is oxygen. This is oxygen. See, there is a sharing of common oxygen with on the both the structures. It is an aluminum octahedra, students. It is a silica tetrahedra. Both were sharing one common oxygen ion. So this sharing between this oxygen ion will keep this structure very stable and strong. This is the reason why this is very strong. And also between these two layers, this aluminum octahedra, silica tetrahedra, and between these two layers there will be hydrogen bonding. So this keeps this lattice structure, this keeps the mineral very stable and strong. This is what I explained here. This is what given a theoretical explanation. And also the crystal lattice, these both crystal lattice will be held by the hydrogen bondings. And another example for this kaolinite is halloysite, anoxite, and dictite. So this is a 1:1 non-expanding type. This is regarding the kaolinite type of clay minerals. Coming to the next, Montmorillonite. So Montmorillonite is an expanding type, students. Generally, Montmorillonite is nothing but it is sandwiched. So one aluminum octahedra is sandwiched between two silicon tetrahedra. Here also I have said there is a sharing of common oxygen. Oxygen will be shared by the both the structures, both the lattice structure. So this keeps this lattice structure very strong. But in between both the lattice structure, we can see some ions, or sometimes mostly we can see some water molecules will be there. So this property will keep the water will keep this lattice structure expansion and contraction. So whenever there is a moisture, we can say it will be expand, and whenever there is a lack of moisture, we can see it will contract. That means these two layers will become in contract. During that contraction, what will happen? Some minerals, especially potassium, students, so it will be interlocked. So that leads to the fixation. So these are the some problem regarding some problems in Montmorillonite also. Mostly this so even we can expect some isomorphous substitution in silica. Instead of silica in this tetrahedra, we can expect some aluminum, or in octahedra we can expect some magnesium. So this leads to the excessive negative charge, students. So excessive negative charge means what will happen? There will be more CEC. So more CEC means more attraction to the cations. More attraction to the cation means more nutrients. More nutrients means uptake will be very high. So uptake is very high means we can get very good yield. This is always soil science is always a this chain reaction. So always it will interlink up with other things. So this is regarding the Montmorillonite. Okay, this is for a study purpose. And coming to the next, illite. So illite is a non-expanding student. It is quite similar, students, and it also called hydrous mica. So in between the lattice structure, quite similar, students, it was sandwiched. So aluminum octahedra is sandwiched between two tetrahedral sheets, just like as Montmorillonite. But at the same time, in between two lattice structure, we can expect some potassium. Some potassium will be there. But here in interlay, there will be some potassium will be there. So this illite. So this illite is a non-expanding. This is best example of a non-expanding type. So what will happen? Mostly in tetrahedral sheet, 20% of silica is in this subject. In this regarding with this illite, we can expect some 20% of silica is substituted by the aluminum only. So what will happen? The result negative charge, there will be much negative charge will be there. It was satisfied by the largely by potassium ions. So whatever the rest of negative charge is left out is there, that will be satisfied by the potassium. So this satisfaction will leads to this will gives the stability to the elite clay mineral. So and this mostly the properties of elite is completely lies between the Kylenet and Montemorlet. There will be intermediate relations will be there. So it will be like somewhat this because it has a some if you see the structure, it is quite similar to the Montemorlet, but at the same time it is non-expanding. So non-expanding 1:1. So it has some intermediate properties between the Kylenet and Montemorlet. So this is regarding with the illite. Coming to the next, chlorides. So very interesting chloride students. Actually, you see students, it is either called 2:2 or 2:1:1. Okay, how means you can see here one silica tetrahedra, one aluminum octahedra. See students, you should have a good imagination to see this type of image, this type of images. So it is a silica tetrahedra. This is a aluminum octahedra, and again it is a silica tetrahedra. Good. This is TOT for your understanding. So this is this structure you have already seen. At the same time, the same structure will be repeated here, but in between them, there will be some aluminum octahedra will be there. So this gives rise to the it gives rise to the 2:1:1, or sometimes it may refers to the 2:1:1. Mostly, what will happen? Chlorides are basically these chlorides are comes under mostly iron and magnesium silicates with some aluminum presence. Okay, at the same time, so it is completely so magnesium, so we can see some aluminum magnesium will be there. So mostly what will happen, octahedral sheets in 2:1, magnesium will be dominated, and also the crystal units of two silica tetrahedra, these two silica tetrahedra, and two magnesium dominated trioctahedra will be there. You will see, you will read all those things. There will be trioctahedra. What is trioctahedra? What is what is the difference? What will happen when aluminum was replaced with magnesium? There will be excess in negative charge. That negative charge, it's complete. The charge will be excess in negative charge will be there. This is a charge development. How the charge will be developed on clay minerals. We will read in chemistry all those things. And mostly it is also a non-expansive type. Naturally, we can't expect any more expansion with size and negative charge similar to the lights. So naturally, it was somewhat is similar to the lights, and chlorides are mostly fixed with Mont and Mont vermiculite. So we can see some fixed. This chlorides always will be fixed between the Mont and vermiculite. So this is regarding the chloride students. It's a 2:1:1. So you just remember this structure. It is very similar, just like Montemorel. The only difference is that you can see some aluminum octahedra in between these layers. This is regarding the chlorides. And coming to the next, so this is the overall view. Distinguish what are the different properties between hyalinite and Montemorel and illite. Summary of view. You can read this all those things. And surface area, internal surface, we can nothing will be there here. In external surface, it is sorry. Yeah, external surface is 10 to 30. Sorry, external surface 10 to 30 milligram meter square per gram, whereas internal surface area in Montemorlet, because it is expansion type, so there will be 550 to 650 internal surface area because it is expanding type. And external surface area we can again expect up to the 70 to 120 meters square. And illite, it is a non-expanding type, so naturally there will be no internal surface, and external surface is 70 to 100 meters square. So this is the internal readings. So zero point 0.7, so 7.2 Armstrongs. You can expect around 18 Armstrongs here, 10 Armstrongs. Completely here in KyleNet, the charge is, you will read very in detail about this isomorph substitution and CEC in very in detail, and regarding this cohesion plasticity property also. So this is a pH dependent, and Montemort is octahedral sheet. You can see some charges about 0.6, it will be there. The tetrahedral sheet, you can see one. So this is a complete, whatever I have said in my previous slides is a complete summary of this lecture. Shapes will be there in hexagonal crystals. Here it will be in flakes model. To understand these hexagonal crystals. You know what is the meaning, how this crystal will looks like. Because in last class I have explained about what is hexagonal crystal. And flakes, this is one type of one. It will give some flakes shape. A shape is shape flakes crystal shapes. This is regarding the shape. So these are the distinct properties of clay mineral students. So with this, thank you students. Very small lecture. Thank you very much. If you have any questions, you can ask now.